Okay, so here we go. So last time we were talking, forgot to pull the screen down. We were talking about integrals in different coordinate systems. The only one we got to was polar coordinates. But we at least kind of laid some groundwork for spherical coordinates and cylindrical coordinates. But anyway, back to polar coordinates. Let's talk about how to compute this integral right here. I'm going to first show you a couple of attempts that will fail. Right, so the very first method is that I'm going to note is to say, well, you could just compute the integral on kind of the big disk here, right, and then subtract the integral on this small disk, right? And if you were to take the whole thing minus the part in the middle, then surely that would leave you with what we're actually interested in here, the annulus. That difference, like that, right? Seems like an attractive approach because each one of those disks seems like a nicer domain. Here's the problem: neither one of these integrals is defined. Neither one of them, and the problem is that if you look at the integrand over here. This integrand fails to be defined at the origin, right? There's a nasty, let's see here. So at the origin, right, there's just a problem. Doesn't make any sense. No, there is no value for the integrand there. And integrals are finicky things, right? It's if you have a singularity somewhere in your domain, well, then it's just not defined. Right? Now, it's tempting to say, well, we could use something along the lines of improper integrals to deal with this. Harder than it sounds. There's some pretty sticky wickets involved in defining improper integrals for double integrals. It's not so bad for single variable integrals. Right? There's things that you can do, but there's some ugly questions when it comes to multiple integrals. So, punchline: this is not a good approach. Okay, next thing you might do, you might try, is to take the domain and chop it up into pieces, right? And so we have, on the one hand, there's that piece, and then there's that piece, and then there's this piece, and then there's this piece, right? There's 4 pieces, and you can compute each one of those integrals. But it remains 4 separate integrals. And that's a lot of work. And furthermore, not only is it 4 integrals, each one of these 4 integrals, keep in mind if you're doing this in rectangular coordinates, these these right? All the curved edges, it's all going to give you square roots in your bounds, which means it'll eventually be square roots in your integrals. That means that this is 4 ugly integrals. So also very undesirable. Okay. All right, so by far the best approach here is to use polar coordinates. And no big deal. We can look at our slices. Let's think about theta slices. Theta slices kind of go like this, right? And you can see that they sort of just go all the way around. We start at theta equals 0, and then it goes all the way around, and it ends. I mean, you're going to want to say it ends in the same direction, but just keep in mind that theta has been increasing around an entire loop there, and so when it gets back to this same direction, you've actually gotten up to where theta is 2 pi, right? So this is 0 to 2 pi for theta, and then for any given value of theta, we can talk about the range of values of r, and r starts at that point, which is on that curve, which has that equation, right? Remember, that's how we do this, right? We identify relevant points. What curves are they on, or surfaces, what have you? What is the equation of said curves? And then we solve for what we're interested in. Here, again, we're looking for r, so you solve for r, and that's, again, an easy one, right? And then our ends, last value of r, is at that point, which is on that curve, which has that equation in which we solve for r, again, very easily. So, nothing to it. Even better, I don't know, anyway, also good, is that when we put in, and again, don't forget to do this Don't forget to write down RD theta all at once, right? By doing so, that factor of R that comes in cancels with the R in the denominator there, and it just falls apart into nothing, right? Effortless integral to compute. Okay. All right, how are we doing? Okay. All right. Okay. So another big vote for polar coordinates. Here's another example. We're going to look at the part of this disk that's outside of that disk. So our domain is what I have shaded here. It's kind of a sort of a crescent moon, you might say. And again, this would be an unfortunate thing to do in rectangular coordinates. I think it's fair to say that the best case scenario would be something like this, where you'd have that piece and then this piece and then that piece. Right, 3 separate pieces. Or you could slice, I suppose, the other way, and you'd have that piece, and that piece, and that piece. So it's bad either way. Okay. So, let's use polar coordinates, and there's a couple of little tricks on this. Here's what theta slices look like. So you can see the first slice and the last slice. And let's think about what we can say about the theta values there. I'll start by looking at theta 2 arbitrarily. That's the point that I need to understand. That point, however, is on 2 curves. On the one hand, it's on this curve, r equals 1. It's also on this other curve, r equals, let's see, what is that curve, by the way? This is, it's a certain circle. We've got the equation for the circle, and you are eventually going to have to do the conversion where you convert that rectangular into polar, and so here's that polar equation. And you can then solve within this pair of equations, you can solve for theta, and that's fine. Not a problem. Here's the, I think, a little bit more efficient, a little bit more clever, a little bit more convenient way to do it, is to notice that this point, a couple of things I can say about it, that is a radius of this circle, that is a radius of this same circle, and that is a radius of that circle. So we've got here 3 sides of a triangle. All 3 of those sides are radii of circles of known radius. So all 3 of those are 1, and that makes this an equilateral triangle, and therefore we know what this angle is. This angle is pi over 3. Everybody see that move? It's a slick move. Clever little trick. Good tool for your toolbox. Every so often, this kind of thing comes. So just be on the lookout, when sometimes nice things happen. Okay. All right. Ditto. This point down here, sort of our starting value of theta. Very analogous argument. Got a bunch of 1s there for sides, and so that's negative pi over 3. Is everybody with me? Okay. Yeah.
Just to be sure, on drawing this,
Yep.
The first kind of part of R is the R equals 2 cosine theta, and then the second part is the R equals 2.
That's right. So what we've got here, this says the collection of points whose distance from 1, 0 is less than 1. So that gives me sort of all of these points. And this says over here, but I'm going to exclude every point whose distance from the origin is less than 1. Right? And so that means I'm going to scratch off all of this, thus leaving me with the gray shaded area. Yep, great question. Yeah. Anybody else? All right. Okay, so let's see. So we've got our theta range now. We've got theta going from negative pi over 3 to pi over 3. And so now let's look for a given theta. Let's look at R. R starts at that point, which is on that curve, which has that equation. Solve for R. Right? The ending value is at that point, which is on that curve, which has that equation. Thankfully, we've already done the algebra on that. This is going to happen pretty regularly, by the way, that you'll have to convert given rectangular equations into polar equations because you need r in this case, right? Polar coordinate. So again, point, curve, equation. Again, reminder, we're looking for values of r, and so we solve for r in that equation and get 2 cosine theta. Everybody happy? Okay, so again, a couple of reminders. When you write down your dr d theta, don't ever write down dr d theta by itself. Too easy to forget, right? All the geometry and trig and clever arguments that we're making about bounds, super easy to forget this if you don't write it down as you're writing down the differentials. So please, please, please do that. Also, of course, don't forget to convert the stuff that's in the original integrand. I mean, this x, you can't just leave it as an x. X is, when you switch to polar coordinates, r cosine theta. Okay. All right. So this next example is, I'm going to say, kind of historical interest. It's really cool argument. This is very, very clever. The question that we're going to face is how to compute this integral. That's a single variable integral, and you might be thinking to yourself, wait a minute, why are we doing single variable integral in a multivariable calculus class? This is, I'll say, a very hard integral to compute, but also really important. So this integrand you recognize, e to the negative x squared, you might recognize, I should say. So this e to the negative x squared is an example of what's called a normal distribution, and it's extremely important in statistics. It turns out it's a very natural, not just mathematically natural, but physically natural. The normal distribution shows up in the physical world kind of for mathematical reasons in a way. But very important in the physical world, very important in lots of applications. And probabilities are computed with integrals. And so knowing this integral is a big deal. It's something you need if you're going to be doing statistics. You'll also recall that the fundamental theorem of calculus doesn't help us here because there's no antiderivative for this integrand that we can write down. So, nasty problem. Here's the really brilliant idea, and this does go back a couple hundred years, but this is a very, very clever concept. And the surprising move to compute this integral is instead to compute its square. Compute it times itself. And it turns out that this seemingly harder problem of computing j squared is actually easier, weirdly. And here's how that works. First of all, let me recognize that this is j squared. There's a j. Now this looks a little different because it's got a y dummy variable instead of x, but it's a dummy variable. Right? The value that the integral ends up being is independent of the letter of the alphabet that you use to represent the variable, right? Of course. Okay. All right. So now let's look at this integral. For the purposes of that y integral, this integral here is a constant. Of course it is. It's j. It's a number, right? And so I can whip that into, inside of the blue integral for free. All right, now let's look at let's see here. Let's look at this integral. Remember our rule: when you have an integral inside of an integral, variables that are further to the outside are constant. Right? For the purposes of the dx inside integral, y is constant. That means e to the negative y squared is constant, and I can whip it inside of the x integral. It's a little bit of a weird move, but it works. Yeah? Again, this is one of these examples. Don't look for instincts of, what would have made me think of this on my own. No, this is too clever for that kind of thing. But make just what you're looking for here is to follow the individual steps. Okay. Okay, so moving along, now we have an iterated integral, and of course iterated integrals are equal to double integrals. You just have to look at the bounds, and you can see y ranges over all possible values, x ranges over all possible values. That means that our domain here is all of R2. Okay, so I've rewritten the question of what is j squared as a double integral. And I'm then just going to compute this double integral by different means. I'm going to compute this double integral with polar coordinates. And, well, dA is r dr d theta. If you're in R2, then theta goes all the way around, and then for any such direction, r is just going to go all the way from 0 to infinity. That's all of R2. Right? So I've just rewritten it in polar coordinates. I've rewritten the x squared plus y squared as r squared. So here's the polar coordinate version of the integral. And what you're going to notice about this, though, is that it's an easy integral. Right? Because of the r right there. The stretching factor that we stuck in there as we must because of change of variables, all of a sudden, there's an easy substitution. Just let u equals negative r squared. Right? There's the r that you're going to need to make the dr actually work, and it falls apart no problem. I mean, technically you have to take a limit as, k approaches infinity or, what have you, right? But it works out no big deal. And the value of this integral is pi. And don't forget, we were computing the square of what we actually wanted. So with j squared equaling pi, that means that j, this integral, very important integral that we need, is the square root of pi. Super clever. Super, super clever. All right, so thank you, polar coordinates. All right. Okay, so that's enough for polar coordinates. Let's move on and talk about cylindrical coordinates. We've already computed the stretching factor. We already know that doing an integral in cylindrical coordinates is going to mean do a change of variables and then think about what the slices look like without actually drawing the pullback, right? And it's not hard to see what those slices look like. There's your theta axis. A constant value of theta is just going to be a plane hinged on the z-axis. Think of it like a door kind of swinging, where the hinges of the door are on the z-axis. I like to call that a plane hinged on the z-axis. Half plane, I suppose. All right? That makes sense to everybody? Okay. Likewise, we can talk about what R slices look like. There's our R axis. There's a constant value of R, aka an R slice. Well, I can draw a constant value of R over here, too. It's part of a cylinder. Right? Thus the name cylindrical coordinates. So that's what R slices look like. And conveniently, we can also, arguably more importantly, talk about what do you get if you take a theta slice. What do you get if you take an R slice of a theta slice? And I think I can persuade you that an R slice of a theta slice is going to be just like a sort of a line segment. The way a half plane intersects with a part of a cylinder, they're going to intersect in a little line segment, a little vertical line segment. All right. Okay, so with that in mind, we're going to proceed and just start doing integrals in cylindrical coordinates. Don't forget, of course, it's change of variables. What we're honestly doing is change of variables. So, yeah, there's a pullback, and I suppose technically there is a pullback domain, and I suppose you could actually draw that pullback domain, but you don't need to. We're just going to look at what the slices look like in XYZ space and figure it out from there. There's a few tips. While there are 6 different ways to order the differentials, these are the 2 that are overwhelmingly the best choices. Overwhelmingly. The way you remember them is that these are the 2 that have dr d theta next to each other and in the usual polar preferred order. right? So DRD theta, always next to each other. You can have the DZ on the outside, you can have the DZ on the inside, but these are the two primary choices. Again, not that there aren't some obscure counterexamples, but I'm going to say that for Math 219, there's no benefit to slicing in any of the other four orders. Okay. All right. Again, you gotta watch out for forgetting the stretching factor. It's extremely important. It costs you lots of points if you forget the stretching factor, and it seems a little weird at first thought, right? But if the stretching factor isn't there, if you forget to put that R in there, then I can't distinguish your paper from a student who doesn't understand that there is a stretching factor, right? So it's extremely important to get it in there. So the way to remember it is to have a personal habit, right, procedure, and this is one of my personal rules. I don't ever write down DRD theta dz as part of an integral unless I precede it by, in advance, putting down the R factor. So I always write down R DRD theta dz all at the same time, and that's a big help. So again, I urge you to do the same. And then again, we have our usual process of how to find bounds. You identify the relevant points, look at the relevant geometric objects. They have certain equations, solve for what you want. Okay. All right, so highly analogous. Let's just dive in and see an example. Here we go. We're looking at the upper half ball of a given radius. So we have a ball centered at the origin. We're going to chop it in half, let the bottom drop off, right? Just looking at just the top half of this ball. This is a solid ball. Right? Okay. And for no particular reason, I'm going to use this order for my differentials. So notice d theta on the outside. So that means I do my theta slicing first. Here's a theta slice. We got to play the usual game now. We got to think about how does that theta slice intersect our solid, and it intersects our solid in these kind of quarter disc slices like that. Is that cool? I think it's a reasonably easy pitch that these go all the way around. Now this is geometric intuition, right? I just have to appeal to the picture and your visualization of the solid represented by this picture. Goes all the way around. Okay. All right. So theta 0 to 2 pi, and now we focus our attention on a single theta slice. So again, here's a whoops. Do reasonably well here. There's our theta slice. Next question, what's the range of values of R? Keep in mind what our R slices look like. R slices look like this, except that we don't care about the whole R slice. All we really care about is how does the R slice intersect our theta slice. We want to know the R slice of our theta slice. And that intersection, I think you can see, is just a little line segment like that. So where do these start and end? Well, first one's there on the z-axis where R is 0. Right? The last one is, well, it's there. And now here's where we have to think geometrically. We have to let the picture be our guide. What do I know about this last slice, this point here that is that last slice? By the way, what are we trying to solve for? It's easy to lose track. We're looking for values of R. So, well, conveniently, at that point, I know what R is, because R is actually a radius of the half ball that we've been given, and so that is A. So our upper bound for R is A. How we doing? Everybody's happy with that? Okay. Alrighty. So, okay, so that means R goes from 0 to A. And then, let's see, lastly, now we're keeping in mind, focused on our R slice of our theta slice. Don't care about the rest of the solid. We just want to look at this R slice of this theta slice. Want to know now range of values of Z. Z starts at that point. Well, again, picture that point. That's where I chopped. That's the bottom of the half ball. That's in the XY plane. It's where Z is equal to 0. And so Z is 0. Right? So again, sometimes they're easy. Lower bound for Z is 0. Upper bound for Z comes from this point. Here's where we have to do a little bit of actual work. That upper bound, what can I say about that point, defining our upper bound of Z? Well, it's on that sphere. The picture tells, right? So again, you got to have a good picture. So on the sphere, that sphere has that equation. That's the cylindrical equation now for the sphere. So, side note, in general, you might have to first write down the rectangular equation and then convert to cylindrical to find the cylindrical equation. In this case, we happen to remember that one from a long time ago. Reminding ourselves that we're looking for a bound for Z. We need to solve for Z in that equation. And solving for Z in that equation gives us our upper Z bound. Everybody happy with that? Okay. All right. Okay, now I did this first example with the you might say the DZ on the inside. Now I'm going to take the exact same example, but I'm going to put the DZ on the outside just to see how it kind of looks different. Again, it doesn't really matter. Sometimes it does, and feel free to decide. Excuse me. Feel free to decide between these options by looking at the various equations and asking yourself, like here, would I rather solve for R as a function of Z or Z as a function of R? You can see here I don't really care. It's kind of the same either way. But sometimes you might, and if it might be easier to solve for one as opposed to the other, then let that guide you for sure. Okay. In this case, it doesn't matter. Z on the outside, we look at our Z slices. That's what a Z slice looks like. It gives us a kind of a disk. And not hard to see where the first and last are. The first one is down here. Well, it's this whole thing, right? But it includes the origin, where it's convenient to just say, well, the Z is 0. The last one is the North Pole. The North Pole is where Z is A. Then we focus on an arbitrary Z slice. Let's see, well, I guess that's fine. On an arbitrary Z slice. Let's see, now we're looking at theta. What do theta slices look like? Well, theta slices are like this, but keep in mind, I don't need the theta slice of the whole solid. I want the theta slice of the Z slice. And the way this theta slice cuts that Z slice is to make, well, just a little line segment. There. And again, geometric argument, appeal to the picture. I think it's a pretty easy pitch. This goes all the way around, so theta goes from 0 to 2 pi. Yeah.
What would a case look like where your theta is dependent on the other variables?
Yeah, so let's see here. If you had, what would be a good example of that? Yeah, those are going to be weird examples. I don't have one prepared, but they don't come up super much. Theta won't always go all the way around. Sometimes theta just goes from 0 to pi. Sometimes it's from pi over 2 to 3 pi over 2, right? It depends on the scenario. It's a good question. Yeah, doesn't happen a lot. Yeah. Right. Never say never. Okay, so we've got theta slice of our Z slice. Now we're just looking at this little line segment, and for that little line segment, dr, right? What is our r range? R starts on the z-axis where r is 0, and then r is going to end, well, let's see here, that point. And what can I say about that point there? Well, it's on our sphere. Right? Again, thank you, picture. I have a picture to be able to identify what you know about which points which serve which roles in your integral. That point is on the sphere, which again has that equation. Now keep track, though. What are we solving for? Here we are solving for r. In the last example, we had to solve for z. Here we're solving for r because we're looking for r bounds. And so we get that. Everybody on board? All right. Okay, so let's do spherical. Same deal. We're going to see the coordinate slices in the XYZ space because it makes life easier. We don't have to deal with actually drawing the pullbacks. We can see everything we need about the pullbacks in our existing picture. So what do these coordinate slices look like? Well, again, a theta slice perpendicular to the theta axis. Again, half plane hinged on the z-axis. It's the same theta from cylindrical coordinates, so same slices. Let's see here. What do phi slices look like? There's the phi axis. Here's a phi slice. Constant value of phi, of course, represents a cone. Right? Think about it. The collection of points whose angle off of the z-axis is the same makes a cone. You might call it a half cone, I suppose, because we're not including the part below. So that's weird. But again, keep in mind, I don't actually care about phi slices. What I'm really going to care about mostly is what is a phi slice of a theta slice. And if you think about that geometry, right, what happens if you take this half plane hinged on the z-axis and intersect it with a cone like this? What you get is little straight line segments, kind of like that. Right, so in practice, theta slices are like this. Phi slices of theta slices look like this. They're little line segments, kind of angled, from the origin, angle measured from the z-axis. And of course, rho slices, right? A constant value of rho is actually a half sphere. Yikes. Right? That's a weird kind of thing to think of as a slice, but that's a constant value of rho there. And good news, again, we don't actually care what that looks like. What I'm going to be needing is rho slices of phi slices of theta slices. So there's a phi slice of a theta slice. And so rho slices of that, as you would sort of expect, just represent kind of moving along that segment. Yes?
So the different heights for the phi slices are arbitrary, right? It's just to make the picture look.
Oh yeah, that's right. I drew these as being as kind of this one I drew as being lower just because otherwise it would have taken up half the page. Mm-hmm. Yeah, that's right. No, it's just angles. Yeah, totally. Good question. All right. Okay, so again, a couple of tips. Again, good news. Almost always, this is the order that you want to order those differentials. Practically always. Yeah, if I wanted to really, exert the effort, I could come up with an example. I'm sure I could. But they hardly ever happen. In practice, this is the way to do it. And again, for Math 219 purposes, if you always do it this way, nothing bad will happen. So I'm going to say just do it this way, right? Always d rho on the inside, d phi second, d theta on the outside. Okay, and notice this is the order that I was kind of implicitly suggesting above, that we start with theta slices and then phi slices of theta slices. and then, keeping track of rho as I move through that phi slice of that theta slice, right? Okay. Second, don't forget your stretching factor. So important. Again, as a exam grader, I can't distinguish someone who forgot the stretching factor from someone who never heard of the stretching factor, right? So it's so important to put it in there. You can think of that, by the way, if you want to be a glass half empty kind of person, you could think of that, so many points to take off for one little mistake. Glass half full, you get so many points for the mere act of writing down the stretching factor. That's it. And it's always the same. It's always rho squared sine phi if you're doing spherical coordinates. It's free money. Right? So don't leave that money on the table. Make sure to remember it. And again, the way you remember it is to always write all of this, namely, always attach your stretching factor to your differentials. Write it down all at once, all at the same time. Don't ever write down d rho d phi d theta by itself. Why would you do that? You're just setting yourself up to forget. Costs you nothing to write it all down all at once. So I encourage you to kind of think of this, memorize this thing, rho squared sine phi d rho d phi d theta. Just like that should just roll off your tongue instinctively. Right? And always write that down together. Okay. All right. And then again, our usual process, identify the relevant points. Those points are on certain surfaces. Those surfaces have certain equations. That's all typical. Let's dive in. So suppose we have a ball, as described here, sort of sitting on top of the XY plane, sitting on top of the plane at the origin. So center up here on the z-axis. Okay, all right. If that's our domain, here's a theta slice. Right? Notice that theta slice looks kind of like this. It's a half disc, and I appeal to your intuition for the picture. Goes all the way around. So 0 to 2 pi. Okay. All right. So before we go on, I have a suggestion. This is just a suggestion. Looking at, let's see here. I'm going to take this seriously. Looking at this theta slice, I'm going to suggest that we redraw it as seen from perpendicular to it. I find it, this is just me maybe, but I find it awkward to look at the way we've drawn this theta slice here, and we've got a kind of a weird perspective thing. It's kind of hard to see like this angle right here, that's pi over 2, but it looks like it's down. You know what I mean? I find that uncomfortable. So I like to redraw the picture. If I feel like I maybe need the sort of additional help, redraw that picture, and then the slice itself. It's just a little bit easier to see what it actually looks like there, and because I'm looking right at it. Okay. All right. So that said, there's my theta slice. Now let's think about phi slices. Keep in mind, phi slices they come out of the origin. Right. So here's phi slices coming out of the origin, and we got to think about where they start and where they end. And where do these start and end? Well, I think it's a pretty easy pitch that they start at 0, right? And then they kind of move along. And now where do they end? Well, I mean, they kind of keep going as the angle gets closer and closer to pi over 2. These slices kind of get smaller and smaller, but they don't actually stop until you get down here to pi over 2. They just get kind of shorter and shorter. Yeah? Does that make sense to everybody? You got to have the picture. And by the way, I think this would be a harder thing to see if you were looking up here on the original, in 3D, looking at the theta slice. It's just, I don't know, there's a lot going on kind of in this one, and not being able to look straight at it, I find that confusing. Maybe it's just me. Okay, so how are we doing here? 0 to pi over 2. Is everybody happy with that? Okay. All right. By the way, let me show you a landmine. A lot of students will get this wrong and say 0 to pi. The reason why a lot of students just get a little confused momentarily and forget what phi is. Make sure to recall phi is angle as measured from the origin. It is not angle as measured from the center of whatever you're looking at. And that's the thing. A lot of students will do this move right here, and they're thinking about angle as measured from the center of their half disc here. I don't know. There's an allure. I don't think this is necessarily even a sort of a conscious choice. They just kind of momentarily maybe just get a little confused, right? But it's a common mistake, whatever the reason, and make sure not to make that mistake. Phi is measured from the origin. Right, off of the z-axis and from the origin. And that stops at pi over 2. Okay. Right, so then here is our, let's see here, our phi slice of our theta slice. Now we look at rho slices. That point is where it starts. That's the origin, pretty easy pitch. That's rho equals 0. The more interesting one is that point. That point's on this curve, you might say, but honestly, a little bit of an illusion. Let's not forget where this picture came from. That picture came from really kind of redrawing this up here. And so up here, there's what our phi slice looks like. There's that endpoint that we're interested in, and what you can see up here, much more easily, I think, is that it's on the sphere. And so what we really need in order to describe this point is the equation of that sphere. And again, I swept under the rug this sphere. I claim that this is the equation, right? And there's a little bit of work that goes into finding this equation. You've got to start by writing down the rectangular equation of the sphere. That's the old high school algebra 2, and then go through that conversion process from section 1.7. Make sure you can do that, right? That's going to be important when you're doing spherical integrals. It comes up a lot. So again, all swept under the rug here, but you got to make sure that you're good with that part. So that now then solve for rho, and there you go. And we're in business. Everybody happy? Yes.
Would it be obvious if we should kind of convert it to spherical and cylindrical, or is that something we could confuse?
Say it one more time. I'm sorry.
Would it be obvious to know whether to convert it to cylindrical? Or
spherical? To choose between spherical or cylindrical. That's a good question. This one here, you certainly could do either way, right? This would have reasonable slices if you were to do it in cylindrical coordinates. Sometimes the clarity on that will come from one or the other not slicing well. You'll find yourself slicing through a corner or a vertex or something like that. Sometimes you just kind of got to write them down both and look at these integrals that you face and decide which one you'd like better. I don't have any immediate rules for how to distinguish between those. It's other than don't slice through corners and try not to invert functions. So sometimes you got to write them down both and see which one looks best. Yep, good question. All right. Okay. So, a quick observation I want to make. I've said this a million times, but I want it written down for the record. I cannot emphasize enough how important it is to have a good picture. It's really, really helpful. You'll notice that my pictures here are respectable, right? They're not as good as the computer-generated figures that are in the book, sure, right? But when you're taking a test, you don't have computer-generating surface tools, right? So being able to draw, it's just unavoidably important, right? And by the way, that's not a peculiarity of the test. In practice, when you're solving problems, being able to sketch something out, it's just unavoidably important, right? Yeah.
Were we ever graded in part off the quality of our drawing, or is it always just?
No, this is not an art class, right? So I'm not going to grade that way. What I can't avoid, though, is that if I can't reasonably infer from your drawing what you were trying to communicate, then I can't infer what you were trying to communicate, right? So it needs to be good enough that I can ascertain your thought process. And if I can't, then I can't. So that indirectly, kind of, right? But not for the point of judging your art. And so all the figures that I have in my notes, for example, are all plenty good enough. Yeah, right. Okay, so some of you might be thinking to yourselves, well, yeah, but I'm no good at drawing, so get good at it. That's my advice on that. And anyone can get good at it. Yeah, some people come in with the advantage of already having learned that skill. There's lots of versions of this. Some people have already had a course in multivariable. Some people have already had. Of course, everybody comes in with different backgrounds. But you can learn how to draw. There's techniques to know. Right? And my resource for that is, as y'all have heard me say several times, on my YouTube channel I have a couple of videos on it. It's a little over an hour between the two of them of here's the techniques of how to draw and here's how they show up in various explicit examples. I strongly urge you to watch those videos if you feel like you could stand to improve your 3D drawing a little bit. And there's no getting around the fact that you got to actually practice it. And I did this myself when I was in high school, college, that kind of thing, right? I actually gave myself drawing drills, right? And practiced and got invested in and highly engrossed in trying to make the drawing as good as possible. And this is a good thing, right? This will give you better tools as you're trying to solve math problems. I think that's something that everyone should focus on. When you do make drawings, don't try to save paper, right? You need a nice sized drawing. And keep in mind that when you draw something, you're then going to be taking slices, which will be a smaller part of that, and then slices of the slices, which will be a smaller part of that smaller part, and eventually you'll find yourself trying to do math, on a cubic centimeter or a square centimeter sized little picture, and it's very, very hard to make a clear picture and to interpret your own picture clearly that way. So don't be shy about making a good sized picture. Be aware as well, you might need to draw more than one. Those of you who have come to office hours recently have seen me draw a figure for the purposes of learning something about the shape I'm trying to draw, realizing that having learned what I learned, realizing that, my first picture is actually bad in certain ways, instead I redo it. Right? Sometimes, several times, I've gone through, 3 or 4 versions of my figure until I get to one that's as sort of, good as possible. And don't forget, for this purpose, on the exams, you have scratch pages, right? And so, again, don't be shy about using those scratch pages to understand as much as possible before you get to actually doing your drawing. Okay. All right. Okay, another example. So let's see here. Oh, wait a second. We have 45 seconds left. We're not going to get that done, are we? This is a pretty good place to draw the line. We'll draw it right there. Y'all have a good weekend. See you on Monday. Okay, I'm just going to have to... Okay. Oh, yeah, and of course, as usual, don't. I have to stop the recording.